Welcome to our electric motor project. We're team number 4, and well, my teammates are Juan Pablo Lascano, Uriel Lopez, Andres Arroyo, and me, Alfonso Nava. For introduction, this challenge consists in building a homemade electric motor with common materials, of course, that we find in our houses, and then analyze it, like to predict the torque and revolutions it will have using the principles seen in class, and then compare them between the theoretical and experimental values to see the error.
Well, now that we know the objective of this challenge, it's important to talk about the theoretical framework. The next concepts are the key to solve this challenge. That's why we need to know and understand all of them. The concepts are electric motor, torque, current, magnetic field, Lorentz force, right-hand rule, and Ampere's law. I'm going to define some of these and that we consider are the most important. So I'm going to start with the torque, that is a measure of how much a force acting on an object causes that object to rotate. As we can see in this presentation, the final equation or formula is the current times the area in squares of the loop times the magnetic field in Tesla. Also, I want to define the magnetic field because it's very important in our challenge. The magnetic field is a vector field that describes the magnetic influence on moving electron charges, electric currents, and magnetic materials. The unit of the magnetic field is the Tesla. And now very related concept is the Lorentz force. The Lorentz force is a force exerted on a charged particle Q moving with velocity through an electric field and the magnetic field. And here we can see the equation.
And well, for our calculations, we use two formulas, the torque formula and the maximum torque formula. First, we start with this last one. And for this, we need to know the current, the magnetic field, and the area of the loop. And we obtain these values of our motor model. And we verify that we have the correct units. For the area of the loop is a square meter. For our magnetic field is Tesla. And for our current is amperes. We substitute these values in our formula. And we obtain that the maximum torque is equal to 0.00017008 Newton meters. And well, then we used the torque formula in a MATLAB program. And the only difference with this formula is that for our previous constants, we multiplied it by sine of theta. And we obtain this graph that is the torque in respect of the angle. And we get this result that we can see that is the same as the previous one. So that means that our procedures are well done.
We also did an experimental motor. This we did with a type D battery, some enamel wire. Unfortunately, it was too thin, and some clips and some magnets that were from some laptop speakers. Since the wire was too thin, in this case, the gauge, the motor didn't work reliably, and it had problems with keeping revolutions constant. So to get our measurements for the experiment, we checked other similar motors and took a range of revolutions more or less, and we also needed the watts that the battery was sending to the loop, and using the formula for torque, being 9.5488 times the watts, well, the kilowatts, and all this over the RPM, we did get that the motor would have a torque around 0.001606 Newton meters, which is pretty much in line with the theoretical value.
Yeah, as we can see, we had a error between the theoretical and experimental value of 5.91%, that it's almost 6. And we think it's due to 3 causes. First one is the magnet, that we didn't know the exact value of the magnetic field because we used the magnet that has the speaker of a laptop. And well, we investigated the material it was made of, and of course the specification of the fabricant, but it might be not correct, but like the data. So this may cause a variation on the error. The second one is energy loss. It's because, well, you know that there is friction between the two metals and of course with air. And of course we have also a loss of energy because of the resistance of the material to electrical current. And this may cause an energy loss that we didn't took into account in the torque formula. So the torque is lower in the experimental value, but this is not the case, but might be affecting. And revolutions, as Lascano said, we didn't have like the exact revolutions of a motor because we didn't have the machine to measure them. And well, the revolutions that we got was like based on really similar motors, but that didn't have the same measurements as ours. For example, the area changed, and this is affecting, of course, the final result of our torque. But it's not that bad, as you can see, it's 5.91%. So the main cause that we think it's causing this error is the magnet, that we don't have the exact data. And conclusions. The conclusions is, of course, we think that it's an excellent example to have applied and understand the electromagnetic forces, and well, of course, to engineering problems. And we only had one problem, that it's using the materials that we found at our homes. We couldn't go out to look for more, and well, this like limited the development of our motor. But as engineers, we gotta adapt to the limitations of our work environment. And of course, this project helped us to gain more experience and improve as future engineers to adapting and working with the things that we have as engineers should. And thank you, that's all.